If you've spent years studying World War II armor and never found content detailed enough, this is for you. In the spring of 1943, at a factory complex nestled in the Austrian town of Valentin, German engineers were accomplishing something that makes no logical sense when you examine the conditions under which they worked. The Nibelungenwerk facility, named after the mythical Germanic epic, was producing a machine so mechanically sophisticated that it employed technologies most nations wouldn't attempt for another 3 decades. This machine was the Ferdinand, and the story of its creation isn't simply a tale of impressive wartime engineering. It's a story of engineering that defies the circumstances in which it was born. A paradox of precision manufacturing achieved while the industrial infrastructure supporting it was systematically being reduced to rubble. By early 1943, the Allied combined bomber offensive had shifted into a new phase of intensity. The Casablanca Conference in January saw Roosevelt and Churchill commit to the progressive destruction and dislocation of the German military, industrial, and economic system. The British were conducting devastating night raids against the Ruhr industrial heartland, the very region producing the steel, the machine tools, and the precision components upon which German armoured vehicle production depended. American daylight precision bombing targeted specific industrial chokepoints. Transportation networks were fragmenting. Skilled workers were being conscripted to the front. And yet, amid this mounting chaos, German engineers at Nibelungenwerk assembled 91 petrol-electric hybrid tank destroyers. Vehicles with dual power plants driving electrical generators that fed power to individual electric traction motors on each track. Think about that for a moment. Electric hybrid propulsion. In 1943, while factories burned, they installed 200mm frontal armor plates, requiring precision welding that most manufacturers would struggle to achieve under ideal peacetime conditions. They mounted an anti-tank gun so powerful and so precisely machined that it could destroy any Allied tank at ranges exceeding 2 kilometers with first-round accuracy. The Ferdinand wasn't a triumph of German engineering, despite impossible conditions. It was a triumph that, upon close examination, appears impossible because of those conditions. And that's what makes this machine worth understanding at a level of detail that most coverage never attempts. The Ferdinand's story begins not with success, but with rejection. Understanding this origin is essential to appreciating what German engineers ultimately achieved. In 1941, the German Army High Command issued a requirement for a heavy breakthrough tank capable of defeating Soviet armored vehicles and fortifications. 2 competing designs emerged. The competition between them would shape the Ferdinand's destiny before the vehicle even existed in conceptual form. Dr. Ferdinand Porsche, already legendary for his automotive engineering achievements and his close relationship with Adolf Hitler, proposed the VK 45.01P, a heavy tank design that reflected his signature engineering philosophy. Porsche had long been fascinated with electric drive systems, and his Tiger tank proposal incorporated a revolutionary petrol-electric transmission. 2 air-cooled engines would drive generators, which would in turn power electric motors connected to each track. This approach eliminated the conventional mechanical transmission entirely. It replaced it with an electrical power transmission system, offering theoretical advantages in reliability, control precision, and the ability to steer through differential power distribution rather than mechanical braking. The competing design came from Henschel, a more conventional approach, using a standard mechanical transmission. When evaluations concluded in 1942, the German Armaments Ministry, under Albert Speer, selected the Henschel design for production. The reasons were practical rather than technical. Henschel's Tiger could be manufactured using established industrial processes and components already in the supply chain. Porsche's electric drive required specialized components, particularly the electrical motors and generators, that added complexity to an already strained production system. Here's where the story takes its crucial turn. Porsche, confident his design would win, had already arranged for production of 100 VK 45.01 P chassis at Nibelungenwerk. When the Henschel design was selected instead, Germany found itself with a substantial investment in chassis that couldn't be used for their intended purpose. The hulls were built, the running gear assembled, the elaborate electrical drive systems in place. Simply scrapping them, unthinkable given the resources already expended and the increasingly desperate material situation. On May 18, 1942, Albert Speer's Ministry for Arms and Armament ordered development of a new self-propelled anti-tank vehicle. The abandoned Porsche chassis offered a ready-made foundation. Rather than attempting to retrofit them for their original tank role, which would have required redesigning the turret and fighting compartment entirely, engineers would build an armoured superstructure atop the existing hull and mount the most powerful anti-tank gun Germany possessed. The vehicle that emerged from this conversion would carry the name of the man whose vision created it, Ferdinand. To understand why the Ferdinand represents engineering that challenges comprehension, you have to understand its propulsion system. And to understand that system is to confront a technological achievement that seems misplaced in time. The Ferdinand was, in essence, a petrol-electric drive concept, similar to a locomotive, applied to a fighting vehicle. Its powertrain was decades ahead of what other nations were attempting. We talk about hybrid vehicles like they're a modern innovation, Tesla, Prius, cutting-edge technology. But German engineers were building them in 1943 for combat. The system began with two Maybach HL120 TRM engines, each producing approximately 300 horsepower, mounted side by side in the rear hull compartment. These weren't the air-cooled Type 101 engines of the original VK 45.01 P design, which had proven problematic in testing. The conversion to water-cooled Maybach HL120 TRM units was one of several refinements made during the Ferdinand program. These engines were proven designs, already powering Panzer III and IV tanks across every front. They were reliable, well understood by mechanics, and their spare parts existed in the supply chain. Choosing them over the troublesome Type 101 engines was pragmatic, but it also meant redesigning the entire rear hull arrangement to accommodate different mounting points, new cooling systems, and altered exhaust routing. Each engine coupled directly to a Siemens-Schuckert generator. Precision electrical machines weighing several hundred kilograms apiece, manufactured to tolerances measured in thousandths of an inch. These generators converted mechanical output into electrical current, which was then routed through control systems to two Siemens-Schuckert traction motors, one driving each track through a final reduction gear. The elegance of this system is difficult to overstate. When the Ferdinand's driver manipulated the steering controls, he wasn't engaging mechanical linkages or hydraulic systems. He was varying the electrical power delivered to each track motor. Turning required no clutches, no brakes heating under friction, no stress on transmission components. The electrical control system allowed for infinitely variable power distribution, meaning the Ferdinand could execute turns with a precision that mechanical transmissions of the era simply couldn't match. During testing, the VK 45.01 P chassis demonstrated an ability to rotate in place, both tracks moving in opposite directions. Something that would become known as neutral steering and wouldn't be common in tank design until decades later. But let me explain exactly what made this possible, because the engineering is genuinely remarkable. In a conventional tank of the era, steering required physically braking one track while the other continued moving. This generated tremendous friction, wore out brake bands and clutches, and created mechanical stress throughout the drivetrain. The tighter the turn, the more brutal the punishment on the components. A pivot turn, spinning in place, was essentially impossible without destroying something. The Ferdinand's electric system bypassed all of this. Each track motor received current independently. To turn right, the driver reduced current to the right motor while maintaining or increasing it to the left. The tracks moved at different speeds and the vehicle curved. No friction, no mechanical stress, just electrical control. For a neutral turn, rotating in place, the system sent current to the motors in opposite polarities. One motor spun its track forward while the other spun backward. The 65-ton vehicle pirouetted like a dancer. In testing, observers watched this massive machine rotate on its own axis and couldn't quite believe what they were seeing. The tactical implications were significant. A Ferdinand could be positioned behind cover, then rapidly pivot to engage a target without the time-consuming process of backing up and repositioning that plagued conventional casemate designs. It could traverse its gun further than the mount physically allowed, simply by rotating the entire vehicle precisely. The capability existed. It worked. It was decades ahead of its time. Welcome to the Ferdinand's fundamental nature. Brilliance, pushing the boundaries of what 1943 technology could achieve. But here's the thing that makes this genuinely incomprehensible. The manufacturing challenges inherent in the electric drive system become staggering when you examine what 1943 Germany was being asked to produce, and, more critically, what it was simultaneously being denied. Copper, the lifeblood of any electrical system. By 1943, Germany was so desperately short of copper that the regime was melting down church bells, confiscating household brass, stripping copper from civilian telephone networks. The Luftwaffe and Kriegsmarine competed viciously for copper allocations. Aircraft wiring, submarine components, communications equipment, all demanded copper that simply didn't exist in adequate quantities. Ammunition production alone consumed tens of thousands of tons annually. Every shell casing that left a factory represented copper unavailable for anything else. And into this crisis of scarcity, German engineers proposed building 91 tank destroyers whose propulsion systems depended on massive copper windings in 4 precision electrical machines per vehicle. 2 generators, 2 traction motors, each requiring substantial windings capable of handling the electrical loads necessary to move a 65-ton vehicle. The absurdity cannot be overstated. Germany didn't have enough copper to maintain basic telephone service in many regions. Yet the Ferdinand program consumed copper that could have produced thousands of artillery shells or hundreds of aircraft electrical systems. That the program proceeded despite this allocation nightmare suggests either Porsche's extraordinary political influence with Hitler, a strategic decision that the anti-tank capability justified the resource expenditure, or simply bureaucratic momentum of a program too far along to cancel. Whatever the explanation, the copper consumption of the Ferdinand represents wartime resource allocation that borders on the inexplicable. And yet, the vehicles were built. The electrical systems functioned. The copper was somehow found. The generators required not only copper, but precision-machined components, depending on machine tools and skilled technicians, both of which were being bombed, conscripted, or simply worn out through overuse without adequate replacement. The control systems required electrical components whose manufacture demanded stable power supplies and clean factory conditions. Conditions that became increasingly rare as bombing disrupted electrical grids and scattered production facilities. That 91 complete petrol-electric powertrains were manufactured, assembled, and successfully installed during 1943 isn't simply impressive. Given what we know about the deteriorating state of German industrial capacity during this period, it's difficult to explain using conventional assumptions about wartime manufacturing. The precision required was extraordinary. The components were specialized, the materials desperately needed elsewhere. And yet, the vehicles were built, and they worked. The Ferdinand's armament was the 8.8 centimeter Pak 43/2L/71, a weapon representing the apex of anti-tank gun development during World War II. Its installation created integration challenges that further illuminate the sophistication of German wartime engineering. The designation L/71 indicated barrel length relative to caliber. 71 times the 88mm bore diameter. That yields a barrel over 6 meters long. Picture that for a moment, a barrel of extraordinary length requiring precision manufacturing that challenges the imagination. This extraordinary length was necessary to achieve the muzzle velocities required for the gun's ammunition to defeat the thickening armor appearing on Allied vehicles. Particularly Soviet heavy tanks like the KV series and the emerging IS designs that were beginning to appear on the Eastern Front. The Pak 43 fired a Panzergranate 39/43 armor-piercing round at muzzle velocities exceeding 1,000 meters per second. That's faster than most rifle bullets. Fast enough that at combat ranges under a kilometer, the round travelled on an essentially flat trajectory. This simplified gunnery calculations dramatically and enabled first-round hits that shorter-barreled weapons simply couldn't achieve. Mounting this weapon in the Ferdinand required solutions to several engineering problems. The gun's recoil forces were immense, several dozen tons of rearward impulse with each shot. These forces had to be absorbed by the recoil mechanism and distributed through the vehicle's structure without damaging the electrical systems packed into every available space, without cracking welds, without sending the entire machine rocking backward on its suspension. The fixed superstructure design meant the gun couldn't traverse the way a turret-mounted weapon could. It moved only a few degrees left or right. This limitation was deliberate, a consequence of prioritizing the massive frontal armor protection over flexibility. The crews learned to aim the entire vehicle using the electric drive system's precise steering, which turned what could have been a crippling limitation into a manageable characteristic. The barrel itself presented challenges that speak to the precision manufacturing occurring under impossible conditions. A gun barrel of this length and caliber had to be perfectly straight, not approximately straight, not good enough straight, perfectly straight, measured in fractions of a millimeter across 6 meters of hardened steel. Any deviation would cause rounds to fly off target. At engagement ranges of 1 to 2 kilometers, where the Ferdinand was intended to fight, even tiny bore deviations could translate to misses of several meters. Every barrel had to be manufactured, inspected, and verified to tolerances that would challenge peacetime production. That they achieved this while production facilities were under attack remains one of the programme's less discussed engineering achievements. The frontal armour of the Ferdinand deserves special attention because it represents yet another impossible achievement under impossible conditions. 200 millimeters of steel, 8 inches. At a time when German steel production was already struggling to meet basic requirements for the war machine. Understanding what 200 millimeters of frontal armour meant in 1943 requires context. The Soviet T-34, considered one of the finest tanks of the war, had frontal armor of 45 millimeters. The Sherman tank protecting American crews had frontal protection of 50 millimeters. Even the Tiger I, the heavy tank the Ferdinand's chassis had originally been intended for, had frontal armor of only 100 millimeters. The Ferdinand doubled that. At practical combat ranges, no Allied anti-tank weapon in widespread service during 1943 could penetrate this protection from the front. Soviet gunners could fire round after round at a Ferdinand's face and watch them bounce away, shatter, or simply dent the surface without penetration. The psychological impact on crews facing this invulnerability can only be imagined. But producing this armor required steel Germany didn't have in adequate quantities. The quality of German armor plate was already declining by 1943 as alloy shortages forced metallurgists to experiment with alternative formulations. Manganese, nickel, molybdenum, all were in short supply. Each had critical roles in creating armor that was both hard enough to resist penetration and tough enough not to crack and spall when struck. The welding of these massive plates demanded equipment and expertise increasingly difficult to maintain. Thick armor requires more heat, more careful preparation, more skilled operators, more time. Time was a luxury German factories increasingly lacked as production schedules compressed and experienced workers disappeared into military service. And yet, the armor was produced, the welds held, the protection worked. In July 1943, the Ferdinand faced its trial by fire. Operation Citadel, the Battle of Kursk, the largest tank battle in human history. Approximately 90 Ferdinands were deployed, with 2 heavy tank destroyer battalions, Schwere Panzerjäger Abteilung 653 and 654. They were assigned to spearhead the northern pincer of the German offensive, tasked with breaking through the extensive Soviet defensive lines built specifically to stop the German armor that intelligence told them was coming. The results were complicated. The Ferdinands demonstrated exactly what they were designed to do. Operating at ranges exceeding 2,000 meters, they methodically destroyed Soviet tanks that couldn't effectively respond. The 88mm PaK-43 punched through T-34s with contemptuous ease. KV-1 heavy tanks were reduced to burning hulks at distances that made return fire futile. Soviet anti-tank guns, the weapons that had proven most effective against German armor, simply couldn't penetrate the 200mm frontal plate. But the Soviets adapted. They'd known this attack was coming. They'd prepared. Rather than engage frontally, Soviet commanders ordered their forces to let the Ferdinands advance, then attack from the flanks and rear with anti-tank guns and infantry assault teams. The Ferdinand sides had only 80 millimeters of armor. Its rear was similarly vulnerable. And the vehicle had a critical flaw that Soviet infantry exploited ruthlessly. It had no hull-mounted machine gun. None. The original design omitted close defense armament entirely, assuming the Ferdinand would always operate with infantry support. At Kursk, that assumption proved catastrophically wrong. Soviet infantry teams crawled through the tall grass, approached from blind spots, and disabled the massive vehicles with grenades, Molotov cocktails, and magnetic mines. Crewmen who survived the initial attacks often couldn't escape. The hatches were designed for a vehicle that wasn't supposed to be surrounded by hostile infantry. And then there were the breakdowns. The Ferdinand weighed 65 tons. 65. Every bridge had to be checked before crossing. Every road surface evaluated. Soft ground could trap a Ferdinand with the finality of quicksand. When one broke down, and they did, frequently, Recovery became a nightmare of tactical proportions. Conventional German recovery vehicles proved inadequate for the 65-ton machine. Recovery teams struggled to retrieve disabled vehicles, and this had to be done under fire, in contested territory, while Soviet artillery searched for exactly these concentrations of recovery assets. The cooling systems, not the electric motors themselves, struggled to dissipate heat during sustained operations in July temperatures while buttoned up against enemy fire. This was not an inherent flaw in Porsche's electric drive concept. It was the result of deploying vehicles into combat conditions before adequate thermal management testing could be completed. Several Ferdinands were lost to fires that appear to have originated in the engine or generator compartments, overheating due to inadequate cooling rather than fundamental flaws in the electrical architecture. German commanders learned from Kursk. After the offensive's failure, surviving Ferdinands were withdrawn and returned to Nibelungenwerk for modification. The conversion addressed the most critical lessons learned from combat. A bow machine gun was added, finally. A simple MG-34 in a ball mount, installed in the hull front, where it could engage infantry attempting to approach the vehicle. The fact that this hadn't been included from the beginning speaks to the design's origin as a pure anti-tank platform. The fact that it was added speaks to the German military's willingness to learn from failure. A commander's cupola was installed on the superstructure roof. The original Ferdinand had given its commander almost no ability to observe the battlefield while buttoned up. The new cupola provided periscopes offering 360-degree vision, letting commanders spot threats approaching from any direction. Wider tracks distributed the vehicle's weight more effectively across soft ground. The original tracks had proven inadequate for the muddy conditions prevalent in Russia. Wider units reduced ground pressure and improved mobility in exactly the terrain where Ferdinands had previously bogged down. Zimmerit anti-magnetic mine coating was applied to the exterior. This paste-like substance, when hardened, created a textured surface that prevented magnetic mines from adhering to the hull, directly addressing the infantry assault tactics that had disabled so many vehicles at Kursk. The modified vehicle was redesignated the Elephant. That German engineers found the resources, the skilled labour and the factory capacity to conduct this modification program in 1944, when industrial conditions had deteriorated even further, adds another layer to the impossibility narrative. By this point, Allied bombing had intensified dramatically. The transportation network was fragmenting. Raw materials were scarcer than ever. They didn't just build these machines once under impossible conditions. They improved them under even more impossible conditions. The Elephant conversion program produced approximately 48 modified vehicles, which went on to serve in Italy. The terrain there was different from the Russian steppe, more confined, often mountainous, frequently urban. The vehicle that had struggled with the open warfare of Kursk found a better fit in defensive operations, where its overwhelming frontal protection and devastating gun could be employed from prepared positions. These vehicles participated in fighting around Anzio and the subsequent operations as the Allies pushed northward through Italy. The Allied beachhead created a contained battlefield where German forces sought to push the invaders back into the sea. The terrain around the beachhead was flat, marshy, and crisscrossed with drainage ditches. Not ideal for a 65-ton vehicle, but the defensive nature of the fighting changed the equation. Elephants were positioned in prepared fighting positions, with clear fields of fire across the approaches. Allied tanks attacking toward Rome had to cross open ground. The Elephant crews waited. The results were devastating. Sherman tanks attempting to advance found themselves under fire from weapons they couldn't effectively answer. The 88mm Pak-43 could engage at ranges exceeding 2,000 meters. distances at which the Sherman's 75mm gun had almost no chance of penetrating the elephant's frontal armor, even with a direct hit. Crews reported engagements where they destroyed multiple Allied vehicles without receiving penetrating hits in return. The narrow Italian roads and mountainous terrain meant engagements often occurred in corridors where flanking, the tactic that had proven so effective at Kursk, was geometrically impossible. The fixed gun that had been a liability in mobile warfare became irrelevant when defending a specific sector from prepared positions. The weight that had made recovery nightmarish mattered less when you weren't advancing, but holding ground. The fighting around Anzio ground on for months. The elephants became fixtures of the German defensive line, moved occasionally, dug in carefully, their crews learning the terrain intimately. When they fired, Allied tanks died. When Allied forces pushed forward, they had to reckon with weapons they couldn't counter at range. But Italy also claimed its share of elephants. The soft ground near Anzio swallowed several vehicles that strayed from prepared roads. Others broke down in positions where recovery was impossible under Allied artillery fire. And as 1944 wore on, spare parts became increasingly difficult to obtain. So, what do we make of all this? The Ferdinand wasn't just an armoured vehicle. It was a statement, possibly an irrational one, about what German engineering could achieve when conventional limitations were ignored. It was a hybrid electric tank destroyer, built while copper was being stripped from telephone lines. A precision weapon, manufactured while precision tools were being bombed. A technological marvel, created by an industrial base in the early stages of collapse. Compare this to what other nations were doing. Other combatants built tank destroyers that were deliberately simplified designs, accepting trade-offs in sophistication in exchange for ease of production. They were built to be produced quickly in massive numbers, accepting individual losses in exchange for numerical superiority. The Ferdinand represented the opposite philosophy. 91 vehicles of extraordinary sophistication, each consuming resources that could have built a dozen simpler alternatives. Was this wisdom or madness? 80 years later, military historians still debate the question. What's not debatable is this: German engineers achieved something that shouldn't have been achievable. They built petrol-electric hybrid combat vehicles, requiring precision copper-wound electrical machines during a copper famine. They produced 200mm armor plates while steel mills were being bombed. They manufactured gun barrels to tolerances measured in fractions of millimeters, while their skilled workforce was disappearing into military service. Perhaps that's the point. Perhaps the Ferdinand represents something about human capability that defies spreadsheet logic. The stubborn refusal of engineers to accept that impossible conditions require impossible compromises. Or perhaps it represents something darker: the willingness of authoritarian systems to ignore economic reality in pursuit of technological prestige, consequences be damned. Either way, 91 of these machines were built. They fought. Most were destroyed. A handful survive in museums today, where visitors can walk around them and try to comprehend how German engineers achieved what they achieved, while everything around them was falling apart. And most of those visitors will walk away without answers. Because some engineering achievements don't explain themselves. They simply exist, challenging our assumptions about what's possible. The Ferdinand is one of those achievements. Subscribe for more content that respects your expertise and challenges what you thought you knew.